an immense pleasure to introduce Giovane and Nieto from ICMS. We're going to tell us about GKM approach for qualifier. Maybe we can push.
Yeah,
You want to,
like make this smaller.
But also like push this screen.
or you want to pull the screen
Yeah,
down
yeah.
and not have it reflect on the board? You're taller than I am.
So the
Thank
tallest
you.
person in the room.
Yes, the tallest. There we go. Thank you.
All right, so thank you. We'll do some introduction for everyone to hear. This is an ongoing work with Leonardo Cavenaghi, Ludwig Castacola, and Pedro Muniz that I want to talk about our initial results and the approach we are doing. So the idea here is that we want to use GKM theory to study normal fit and invariant in flag varieties, and then end up applying this to studying complete intersections, right? So I'll start from the very beginning, introducing the idea of normal fitting theory. So we'll fix here along all the talk X smooth projective variety, and I want to talk about what is the moduli space of stable map. So fixing an effective class on the second homology, the variety. We define what a genus-zero stable map is. That is a map from a project connected nodal curve, genus-zero, at worst nodal, to X that has some marker points on it, and that is stable in the sense that the automorphic group of this map is finite. Right? We define the moduli space of stable maps to be all such curves that have push forwards for chosen class. Okay, this defines the linear Mumford stack, and this is important because then we can define what is the virtual fundamental class. Okay. The idea of defining this virtual fundamental class is to replace the fundamental class of the variety, or not the variety case necessarily, to do integration. So we can define the normal fit invariant. Do it this way. We define the evaluation maps given a curve, a pre-stable curve, sorry, a stable curve. The evaluation maps just evaluate in the IF components of the IF market points that we chose. Right, so we can do pullbacks of this map and define what are the Gromov fit invariants. So given say n cohomology classes, we can pull back each one of them and integrate over the virtual fundamental class. And these are the Gromov fit invariants. Right? So in general, these are pretty hard to compute. But I'll talk about some methods that we have to compute them in flag varieties. But first, I want to say what do we want to do with this. So in the end goal here is to do atoms, right? So for that, we want to talk about quantum multiplication that is defined from Gromov-Witten invariants. So the first part is to define the Gromov-Witten potential. So given a cohomology class gamma, we define the Gromov-Witten potential to be this expression, where gamma n is just taking the Gromov-Witten potential of gamma n times. Okay, this depends, of course, on the class gamma. And to be easier for computations, it's usual to express gamma in coordinates. So pick a basis for your cohomology, so T0 is just the identity, basis for H2, and then you complement your basis for the whole cohomology to it homogeneous, right? So in this basis, we can write any cohomology class as in coordinates, right? So I can write or gamma as epsilon for some coordinates here. And we can just expand this using some Gromov-Fit invariant axioms. And well, this would be in the end the expanded expression for the Gromov-Fit potential. Something that we call the classical part. That is that will be sorry, the part that will give us the regular curve product. And this is what we call the quantum part. Okay, so this is just the expanded expression. Here we have the Gromov-Fit potentials of some cohomology class, the basis that is picked, and you have some coordinates here. Right? It's a big expression, but it's just so we can, having coordinates, we can take derivatives of this coordinate. Formal derivatives, of course, because these are power fields. So the quantum product between two cohomology classes in the basis that we picked is just the third derivative of the potential in this coordinate. And this gives us the expression for the quantum product, or actually what we call the big quantum product. So I want to note here that this depends on the class that we chose to do the quantum product, the class gamma. That's why. So let me just say the potential depends on the class gamma, right? So we have different quantum products depending on the classes that we chose. All right. And this defines a ring, right? So if we take the cohomology times the space, the formal Fourier series in coordinates, we get an algebra, and the identity of the cohomology is still the identity in this quantum product, and this operation that we define is commutative and associative. Okay? But in general, it's very hard to compute these big quantum products because it's a formal Fourier series. There are no general results on convergence or anything. So we tend to avoid doing it and do instead what we call the small quantum multiplication. Okay? So the small quantum multiplication is defined from the big quantum multiplication when you take your chosen cohomology class to be in H2. And this simplifies a lot because it becomes a finite sum and can be expressed in this format. So the quantum product of two guys is just this finite sum of Gromov-Fit of three Gromov-Fit invariants of three cohomology classes. Okay. And why is this interesting? The end goal here is to do atoms. And what are atoms? I'll give here a very simple idea of what atoms are. I'm sure many others will talk more about this. But we want to look at this product here, the first term class quantum product with on others cohomology class, and we want to look at the eigenvalues of this operator. Okay, so if these eigenvalues will depend on the class omega that we choose, and we want to pick the omega that will give us the maximum split, meaning the maximum amount of eigenvalues for this operator, and this will be called atomic representation. Okay. All right, so this is the introduction to what I want to do. But the focus here is to do all of what I just said, so computing Gromov-Fit invariants, computing quantum products in flag varieties, and then applying to complete intersection. So let me just introduce what this is. Flag variety is a homogeneous space where D is a simply connected semi-simple Lie group, complex Lie group, and P is a parabolic subgroup. By parabolic, you can just think that when you're talking about matrix groups, it's just the upper triangular matrix, right? So you have a group, Lie group, and you have the upper triangular matrix. this is the what we call flag variety. Why is this interesting? We have a very strong combinatorial data for flag varieties in the Lie root system. Okay, so we have the so-called Lie root, the root space decomposition. You can decompose the Lie algebra of roots in. We have the maximal torus in our group, and we have the so-called roots. These roots, they completely determine the flag variety. And the idea is that we can express every geometrical property of this variety in terms of these roots, right? There is one other combinatorial set that I've just mentioned what it is. That's called the file group. So we have the so-called roots, and the roots, they are linear functionals in the torus. So linear functions meaning they also determine the hyperplanes, right? So we can talk about reflections of these roots. And those reflections, they create the so-called file group.
You can write to us, well, again, to make in the board, what is this decomposition roots quickly and say how it's connected with the variable. Sorry.
Yeah, so there's an example that we'll be doing here. We can talk in general. So we have always given a flag variety. We have the space of roots. Can you see that? That's
Maybe it's well, now it's
so given a flag variety, the Lie group that we chose has the so-called root system. This is a subset of a finite subset of the linear functions of the torus, right? We usually denote them by alpha, so say something like 1, 2, and so on. And linear combinations of these guys. Right, so this is one important set when you're talking about Lie groups and semi-simple groups. And we have the so-called file group, which is the span of the reflections of these guys. Okay, so by reflection, I just mean, so they are linear functionals, so they determine the hyperplane in the torus, and you can talk about reflections. In the end, the definitions of these guys are not the most important. Important is the combinatorics of them and how they relate to each other. We don't actually use like what is the hyperplane and what's the reflection, just the combinatorics of them. Right? Right. All right. So yeah, one example of like variety that would be the simplest one to use the theory on. In this case of two flags in C3. And by that I mean the space of subspaces. Like V1 here, a one-dimensional subspace, V2 a two-dimensional subspace, and if we take the set of all such subspaces, you get the two flags of C3. I'll give another description of this guy later, but for now this will be a better description for me to do first. So as Lie groups, this is the group SL3 of matrix in 3x3 matrix of determinant 1, quotient by the Birational group, which is the upper triangular matrix, right? So if you can take the maximum torus in SL3, which is just the diagonal matrix, and this determines a torus action in our variety, right? So you can just multiply the subspaces by the torus. Okay, and in this variety, it's worth noting here that the phi group is isomorphic to S3. Okay, so how can we compute the Gromov-Witten invariants for flag varieties? And especially what I want to do here is to compute them for this one.
But what is this three here?
That's right. The
Symmetric group?
symmetric group, that's three, yeah.
Is it just the disposition of them on the
It is. It is.
Maybe just like the three is downstream. Underline three.
Oh yeah, sorry.
otherwise it looks like here.
Here, yeah.
Yeah,
exactly.
yeah.
It should be fine.
Yeah,
The,
yeah.
the old books project estimation D and below
Oh.
50.
I'm old.
Okay.
All right. So how do we want to compute the Gromov-Witten invariant in this time? We want to use a GKM approach. So let me say what a GKM space is. Say you have a smooth projective variety with an effective torus action. We call this space a GKM if it has a finite set of fixed points and an isolated set of one-dimensional orbits. Okay. So if we have such a space, we can define the GKM graph. Okay, so GKM graph would be just the vertices are the fixed points. So every fixed point, you have a vertex, and the orbits, the one-dimensional orbits, will be the edges. So if you have an edge connecting these two fixed points, so if you have a P1 connecting these two fixed points, you have an edge. If you have a P1 connect these two fixed points, you have an edge, and so on. It's just the GKM graph. So for the example that I just talked about, all right, we have this GKM graph. Okay, so I just said that. Let me explain this graph here. So we're talking about subspaces contained in each other, and we want to act on these subspaces by a torus, right? So there's a guy like this, a diagonal matrix in with the terms one, yeah, but a diagonal matrix. So and say that we have our canonical basis, of course, and yeah, I'll tell you what is the one. So what are the invariant points here? Just the points, the subspace is generated by this guy. So, for example, I can take V1 to be the span of L1 and V2 by span V2 some V1. And I can change these guys. I can put E2 here and E3 here and so on. So, for example, this guy I can denote by 1, there's 1 here, 2, I've got the 2 here, and the one that's left, 3. So I can put 2 here, 1 here, and 3 here. So these are the guys that we have here. So we have six points there, all the options that you can make the invariant subspaces, and you have edges connecting them. You have orbits of the torus action that connect them. Right? So it's just an example to illustrate from GKM spaces. So you have fixed points and you have invariant orbits, but I just want to say one more thing about the combinatorial data that we have. They're called Schubert basis for flag varieties. These are very important basis for the cohomology. If when you're on a flag variety, you have this preferred basis that is very well behaved in the cohomology, is the Schubert basis. Okay? So given an element of the file group that I talked about, it can be seen as a subgroup of our group T, and that's okay. And we can define the Schubert cell, this guy here. You just take the point of the element of the file group, and you take the orbit of the for group. You just translate, you just conjugate it so it has matching dimensions, but this is optional. This defines the subvariety, and we can take the closure of guy, and this defines the subvariety. And this is a basis for our cohomology. All right, and you can even say in which degree it is. So it's in the degree of the length of the chosen element. And just by length, I just mean that like the divide group is generated by the reflections. You can like check how many reflections you need to achieve that guy, and this is the length. So we have a chosen basis for variety, and we know where in which degrees they are, and there are many results about how to do cut products on these guys, which ones are containing others, and many other things. All right, so now we want to use the GKM theory. We want to take advantage of the torus action to actually compute Gromov-Vitti invariance. So the idea is that compute Gromov-Vitti invariance is a very hard thing to do. But if you use the torus action, and instead of working the regular cohomology, we work in the equivariant cohomology, we can compute equivariant Gromov-Vitti invariance and then obtain the regular Gromov-Vitti invariance. And for that, we need, for that, because Gromov-Vitti invariants are indexed they are happening in the moduli space of stable maps, we want to parameterize this space when we have a torus action, all right? So I'll just define what is a market tree. So market tree is just a graph. There is actually a tree, right? And it has a set of vertices, a set of edges, and inside the edges we have some market points. Some of the vertices are marked with one point. For each vertices, we attach a fixed point of our GKM space, and for each edge, we attach a one-dimensional orbit of our GKM space. So basically, we're putting labels. Oh yeah, sorry, and we also have a degree of the init edge. So basically, we're taking a tree and we're putting labels on it. The vertices, we are putting labels in our fixed points in our GKM space. In the edges, we are putting labels in the edges of our GKM of the invariant orbit in our GKM space and market point. Right? So
maybe we can do as an example.
Yeah, sure.
For instance.
So a simple example is something like the GKM graph of P2. So it has 3 fixed points. The P1, 2, and P3. And you have 3 lines connecting them. So let's say P1, P2, and P3. So what is a market tree? There's a tree, so we can take any tree. Let's say it be something like this. All right. So to each vertices, we attach a vertices here. So I could put say P1 here, P2 here, P3 here. Well, And to each edge, you touch an edge of this guy. Of course, we still have to maintain adjacent, right? And so the edge that connects P1 and P2 here has to be P2. The edge that connects P2 and P3, P3, and so on. And to each edge, we also attach a degree. So say this is degree 1, this is degree 2, and so on. Okay. And lastly, just market points. It's just very arbitrary. So I can mark this vertices here with 1 and with 2. I can mark this vertices here with the number 3. I can mark this vertex with the number 4. And I can do, say if I have a fixed n at the start, I can do up to n. Right? So this is an example. But where are these guys coming from, actually? Right? They're coming from the moduli space of stable maps. So if we have our stable map here, curve that's fixed by the torus action. Okay, so we can put back torus action to the moduli space. We can construct from this invariant curve such a graph. In this way, the vertices are just the pre-image of the 6-point set. So say I have a curve here, right? The curve C, and I'm taking the map F to my GKM space. I'll just construct this graph in this way. The vertices of this graph would be the pre-image of the fixed points. The edges would be the the connected components of the pre-image of the vertices, right? So the vertices are the pre-image of the vertices, and the edges the pre-image of the vertices of the connected components. So the degree is just the degree, the map, and the markings is just the. So if I have a market point here, that is. If I have a market point here, the vertices attached to it will get this marking, right?
So this T, M, G, M0, and T is torsion variant.
Yeah, the torus variant. Yeah, so it should have written that. Why is this important? Because we have a projection of all the invariant classes, all the invariant stable maps. They're in projection with all such trees. So the idea is that we parameterize this space in this combinatorial set, right? And using that, we propose this formula. So the idea here is that the Gromov invariants, they compute rational curves that passes through some subvarieties, right? So parameterizing all the curves, we are checking the contribution of each curve in the Gromov invariant. So I know the formula looks ugly here, but it's all right. So given some cohomology classes and an effective class beta, I want to compute the Gromov invariant, or at first the Equivariant Gromov invariant of this guy. So you are proposing this formula, which is just taking the sum of all the market trees, all the possible market trees that we have with any markings such that the cohomology classes of all the curves sums up to beta.
So gamma is a market.
Gamma is a market tree. Yeah. So you sum over all the market trees that have any markings, and the cohomology classes of that is sum up to beta. Right? And we have this formula. which just a combinatorial form, right? So, and this would be the full formula, opening up all the expression. Of course, it's a big formula, and these guys, if you think about, you have many of them. So the idea, we develop a program, a software that can compute this guy, at least in the case of flag variant. Okay, what's the idea? Every guy here, so let's say these lambda guys, all of these lambda, they are the characters of the torus action in our GKM spaces. Okay, so pick a fixed point, you have the tangent space there, you can talk about the character of the torus action. All right. The idea is that if you're doing this for flag varieties, we can compute in a general way, not just case by case, how these characters are, what these characters are, and you use that to develop the software that you just need to impute the Gromov written classes that you want to compute the Gromov written, and the beta, and of course, saying which flag variety you are working on, and the software computes all of these Gromov written invariants using this formula. Okay. This is an example here. So we went to the variant that I just talked about, FL3, and it computed all the Gromov written invariants that are important to the quantum multiplication. The small quantum multiplication, yes. So this table here would be the matrix of the quantum multiplications for these variants. Right?
What is I1 and I2? Y1.
Yes, sorry. The second cohomology of this guy has dimension 2. And like I said, the quantum cohomology is dependent on the cohomology class dimension.
Degrees.
Sorry?
Degrees.
Degree.
I mean, it's
Yeah.
like a zip license, like basically.
Yeah. So the second cohomology has degree 2. So the small quantum homology has two degrees to work on. Y1 and Y2. So you can choose which class you are working on, depending on the type. So you can get 6 different eigenvalues in this multiplication if you choose the coordinates one different to the other, but if you choose them, you can get 4 eigenvalues for this quantum multiplication. Right? Well, now I want to start talking a little bit more about atoms and what you want to do with them. So if you have 6 eigenvalues in our quantum multiplication, we can't say anything about personality. Of course, it's a flag variety, so we already know its ratio. So this is not the point. But we can start looking for G actions and start looking if these actions are G linearized. So for this variety in specific, we take this action here. So FL3, like I said, stage 2 subspaces, one containing each other, right? And we can take this map that just flip them and take the orthogonal complement. This defines a Z2 action in FL3, and it permutes the H2 class. All right, so the Hodge diamond in this guy is 1, 2, 2, 1. But if I put this into action, the 2 generators here, they are false. So we have only one invariant guy here and one non-invariant. Of course, the point class and the class of the whole space are invariant, and by the point duality, we have one guy here that's also.
When you say linearization, Equivariant. You mean for subgroups automatically for the for which subgroups? For which actions?
This action is a homomorphism action, but can be so
Final subgroups as well.
finite groups. Yeah.
And did does atom solve this problem in this case?
Well, in this case, what I was going to say is that this decomposition is a
No, not for this group.
Oh.
This variety. For this one. This group is linear. But I mean, for this variety. So if you fix this FL3, if you take all any group acting on this, just out of theory answer is it.
the thing is, if you're looking for a subgroup of the automorphism group, it only has these two action that is non-trivial. That's the only non-trivial action. Trivial, by trivial I mean trivial in the cohomology.
And okay.
Yeah, so this is the only non-trivial action in the cohomology. So if you're acting in with an automorphism group, this is the only one. You won't have another.
Oh, my question is, you mentioned linearization.
Yes.
If I give you some group, final group of automorphism, can you use an atom theory answer its actions? Yes? For any.
I mean, we have to check case by
Yeah,
case.
it's
but-
No, but I mean, just
Yeah.
for this particular.
Yeah, yeah.
So we have a lot of.
It's of course case by case, but that's the ideal
If
time.
you give us the action, we can.
Okay. I'll give.
Okay,
Yeah.
okay.
That's the point. Okay, good. Yeah, this is what we do.
But this is just a baby example here. We can't conclude non-rationality, non-linearizability of these guys. Actually, we can't say if this action is linearizable or not. We believe it is, but we can say this is just to show that we can use the program to compute the Gromov environment. But what is actually the goal? Because flag varieties are already known to be rational, and there are not that many possible actions. So the idea here is to extend this theory to complete intersections over flag varieties.
Input.
Yes, in flag varieties. Right, so what would be a complete intersection? So say we have again a smooth projected variety, and we have a vector bundle over this variety that is generated by global sections, and we pick an action. Oh, sorry, a section of this bundle, and we require that the action intersects the zero section tertiary, right? So we can look at the zero locus of section, and this defines a smooth produced scheme that has the dimension of our initial variety x minus the rank of E. Okay? And this is what we call the complete intersection. Okay? So if we're talking about moduli space of stable maps, we have this inclusion here. So and okay, so we will restrict ourselves to your GKM spaces, because then again, that is to use the transaction to localize the problem. So you have a GKM space X, and again, a vector bundle generated by global sections, and you at each fixed point of the GKM space, you can decompose the fiber in the vector bundle there in some vector spaces, right? And you have the torus action in each of these guys. And then again, we will propose a formula that computes not exactly the Gromov invariance, but almost of these guys in terms of these characters of the torus action, right? So we do this by using the called King crash quantum left screen. So this is again, we're in the same context here. Actually, determining only for its convex vector bundles. But in the same context, we have an inclusion of our complete intersection in X, and this defines, this induces a map between the moduli space of stable maps, right? And we have this theorem here that says that the push forwards of the virtual class in the moduli space is just the notation here is completely wrong, but it's just the intersection of this guy, which is just some Euler class, some Chern class of some vector bundle with the virtual class of original variety, right? So we can use this formula to propose these results. Okay. Again, we are in a GK space. We have an vector bundle. In here, we require that the vector bundle also has a T action. Okay. And if we take a section that's transversely to the zero section, we can get smooth projectority. Right? Okay. And we can compute, like I said, not exactly a Gromov-Witten invariant in Y, but a sum of Gromov-Witten invariants. Okay, so picking a beta in our H2 of X, we can take the Gromov-Witten invariants of all the beta prime that goes to beta with the push forward, right? So again, we propose this form that's very similar to the one we did before. So we just added a small terms for the complete intersection here. Okay, questions about this? And okay, so if you're talking about quantum cohomology or small quantum cohomology, it's already defined to be taking over the sum of all the H2 all effective class, right? So even though we can't compute a single Gromov-Witten invariant, we can compute the sum of all the classes in H2. So we can use this to do small quantum cohomology in complete intersection. Okay, that's what just did. And so just an example here today, I want to do this for the like variety of FL3. So like said, FL3 is just the projectivization of the tangent space of P2. It can be seen many different ways other than the one that I spoke. So in this way, or you can write it in coordinates. Right? So today we want to do a complete intersection over this guy. So in this guy, yeah, sorry. I will think about the vector bundle over it. Complete intersection in this guy. So we will take the square root of the uncanonical line bundle over it. This one is over it.
Yes.
And we want to do complete intersection of that. So this variety is bundle. The vector bundle is very ample. So and it's generated by global sections. So every requirement that we had and some more, like some. This is the Hodge diamond of this guy. So, like I said before, the variety we're working on has this Hodge diamond and dimension 3, and the complete intersection will have dimension 2, right? So a surface. By the Lefschetz hyperplane theorem, we know that the Hodge diamond for complete intersection would have to be something like this, plus some primitive parts that could appear here. Right? And in this case specifically, we got this hot stack. So two of these guys coming from the primitive part and all of the rest from the ambient part. Look, we can use the program to compute the eigenvalues of the quantum multiplication by the first term factor. Right? And this is what we get. Of course, the by the formula that I showed you, and go back to this. Oh, just policy here, guys, will have to be the fullbacks of gamma h, right? So we can compute comorbid invariant of guys that are fullbacks from the formula. So we can compute comorbid invariant of the ambient part, right? So when I say that these are the eigenvalues, you notice that it's 4 by 4 because they are only computing the eigenvalues in the ambient part. So only for this part here, the primitive part, this result came. But because we are in a funnel variety, we know that we have a splitting of the the small quantum product of the ambient part and the primitive part. And also we know that the eigenvalues for the primitive parts are always zero. So because it's funnel, we know exactly we know that the primitive part will contribute with two eigenvalues on zero. Also zero is multiplicity. And this guy there is the ambient part, we have 1, 0, and other three different eigenvalues. So in the end, we are in a variety with 0, the eigenvalues are 0 with multiplicity 3, and 3 other eigenvalues. Okay. So I forgot to say something. So which variety is this, right? So this is called the del peso of degree 6, and it can be seen as so P2 blown up in three different points. So it's realizing this that we know that this would be the Hodge diamond. Right? So this is a rational variety, but then again we can look for group actions on it, and we have a specific choice here that a natural choice that can be made. So this guy, it has this hexagon of -1 curves. So you can rotate this hexagon. So you have this D6 action that is rotating this hexagon of curves. Right? And because of this action, because the way this action is defined, we are rotating all the curves. We can only have one invariant curve. There is the curve determined by taking all the coordinates equals to each other, right? So, and of course, the H0 class and the H4 class are invariant. So you have one class in H0, one class in H2, and one class in H4. They are invariant, right?
Which is this group generated by this two second.
Yeah. So, and because of this, we arrive at this result. So, say we are in the, all right, I just describe the surface to the phase of degree 6. You have this D6 action, and using atoms, we can conclude the non-linearizability of this action. Okay, because like we said, we already have 4, let's say not necessarily atoms, because at first you can have further splitting. Yes, at first you can have further splitting. So they're not atoms yet, but we have 3 invariant Hodge classes, and I'm sure Leonardo talked about this yesterday. Yes, but every atom needs to have an invariant Hodge class. So if you have three Hodge classes and 4 atoms standard, let's say, you cannot have further splitting because you won't be able to have this Hodge class all the atoms. So with that, we can conclude the non-linearizability of this action.
I'm 100% sure. Okay, let me be devil's advocate. Can I interrupt?
Yeah.
This is a cycling group. It fixes a point. Your coordinates point 1, 1, 1.
Yeah.
If you blow up this point, you get the best surface. And through this point, you have 3 quantities passing. So they split become -1. So you contract them. You get P1 plus P1 plus P1. With the action of cycling. Cycling group always takes a point on the way. So it fixes a point. So you project from this point, and you get them up to P2. So it is linearity.
Maybe you can show again the cyclic action. I understand. Maybe
Any cyclic action.
for the six.
The cyclic action,
Oh, it's a 6.
it's cyclic on curves, right?
No. If you have a cyclic group acting, say, on a rational surface, it always takes just by election. So for this case, allow this point, and you can in this coordinate, this point is 1, 1, 1, 1, 1, 1. So this gives you blow it up. You have 3 minus 1 curves, so depends on degree 5. You contract them, you get P1 plus P1. With the action of C6, it should fix points.
Yeah,
And if it's 6 point, you project P1 plus P1 is a quadrant. Project, so you get a map to P2. So maybe you need something more.
Okay, we're gonna check that.
Okay, maybe we might check what the
Okay, that, yeah.
Good stuff. All right, so for today, that's all. Thank you.